The subject that we have for today is working with our basic idea of what the purpose is of statistics. Can somebody tell me what's the purpose of statistics?
Data-driven decisions.
Data-driven decisions. What does that mean?
For trends.
And what else?
I can't remember what it is.
Okay, so yeah, there's something else.
What to expect.
What to expect. What does that mean?
If it's less than 5%, then you don't expect to have above 5%.
Okay. So when we're talking about the purpose of statistics, we're dealing with the question of what to expect. And specifically, what we're going to be talking about today is also the process of statistics. What is the process of statistics?
Using sample data to understand the population.
We use a sample to understand the population. And so then, when we put these two ideas together, we're asking the question, what can I expect from a sample? And what can that tell me about a population? So that if I ask a question like, how many people do I need to interview in order to have a really good idea of the percent of people who are in favor of an issue or a candidate? How many people would I need to talk to in order to find out if Bernie Sanders has a significant amount of support in Wisconsin? How many people would I need to choose at random in order to make that happen? How would I know that? How would I know what to expect from my sample to be able to know about the entire population of Wisconsin? So I want to answer that question. Let's start answering that question today. Okay, so I'm going to start answering that question. So what I'm going to do is I'm going to create three different distributions here. And the first distribution that I'm going to create is going to be for blood pressure. And I'm making up these numbers, okay? So don't consider me a medical expert. But let's just say that I'm looking at population numbers for, let's say, a particular company that has 20,000 people in it. And I'm looking at the population. And when I consider the population, I'm going to say that it's more or less bell-shaped. So this is a bell-shaped data. And I'm going to say that the mean, I'm going to use the symbol mu. Mu is 120. And the standard deviation, which would be sigma, is going to be, let's just say 10. 15. This is the population mean and the population standard deviation. You need to recognize those symbols as being what they are. Now, according to the empirical rule, what would I expect from the population here? If I apply the empirical rule to this situation, what would that tell me about the population? Yep.
That 95% of all the data should be, or I'm sorry, all the
95% of the data
would be between the two standard deviations from the mean.
That's correct. What does that mean here?
And most of the people are in the middle.
No, I've got numbers. I want to know the numbers. Tell me numbers, please.
It would be 90 to 150.
90 to 150. That would be where I would expect 95% of my data. Okay? So I'm just going to put that out here. 90 to 120. Okay? That's what I expect from my data set. But now I'm going to change this. And what I'm going to do is I'm going to take a sample. And when I take a sample, I'm going to take the average of the numbers of people that are in my sample. It's going to be a randomly selected sample from this large population. And for our sakes, let's say that n is equal to 36. If I say that n is 36, that is my sample size. It's really important for me to have that in mind. What is the sample size? 36 people, I'm asking about their blood pressure. And then I'm going to find their average. So I'm going to have the sample mean, and the symbol for that is x bar. So from this population, I get 36 people. I then find their average blood pressure. That gives me a number, which is the sample mean. Then I'm going to do it again. I'm going to go back again, pick 36 people at random, and find that average. And I'm going to keep doing this over and over again. And the question that we need to resolve now, what does that distribution look like? This is called the sampling distribution of the sample mean. So if I'm going to have the sampling distribution, what do we think is going to happen? If I take a sample of 36 people and I find the average, will it always come out to be 120? No. Because it's a randomly chosen sample, it's just not always going to be 120. However, it is going to be centered at 120. Sometimes it might be higher than 120, sometimes it might be lower. But it's going to be centered at 120. So the first major concept when we ask the question, what do I expect from my samples? The first answer is I expect my samples to have an average which is the same as the population. Some of the samples might be higher, some of them would be lower, but I would not expect it to be a skewed distribution. I would expect it to be centered on 120. So what we say then is the mean of the sample means is equal to the mean of the data. Or sometimes we don't put the little X on that one. We would just say the mean of the sample means is the same as the mean of the population. But then the next question is where statistics really happens. This is where the stuff happens right now. And that is, what about the standard deviation of these numbers? If I'm taking 36 people at random, would it make sense that I would have 36 people whose average was 140? It would not, because if I'm truly taking people at random, then how could it be that they would all be to the right and then they would all be that far to the right, so it would be 140? It would not make sense for that to happen. So when I'm taking a random sample of 36 people, I do not expect them all to be extreme values. Because I'm randomly selecting them, I would expect the values to be all the way from the high to the low end of this. And so then, what that means when I do the average of the 36 people, that this distribution will have less variation in it than the population would have. So even though the population has this amount of variation, when I take the average of these randomly selected things, this distribution will not have as much variation. And as it turns out, there are mathematical ways to describe this, that the standard deviation of the sample means will be equal to the population standard deviation divided by the square root of n. And if you want to go figure that out, see how it works, you can. But we're just going to believe it for right now. That's the formula. So right now we have this thing which is centered at 120. But now I want to know what this number is. What is the standard deviation divided by the square root of the sample size? So this would be 15 divided by 6. What is that? 2.5. So I guess, Jeff, you're going to have to stop answering questions because you reached your limit. So now the question is, what does the empirical rule tell me about the sample distribution? If I'm going to use the empirical rule, what numbers would be in my what to expect section?
You'd expect that the data values should be between 115 and 125.
Between 115 and 125. So this is how statistics works. Based on this information, I'm able to say that even though this population has a fairly wide distribution of numbers, the sampling distribution is fairly narrow. So even though samples are not accurate, in the sense that I'm not going to get exactly 120, based on my sample size, I can know how accurate they are, actually. So that I can say, I would expect them to be between 115 and 125. But there's something missing from what just happened. When does the empirical rule apply?
When it's bell-shaped.
When it's bell-shaped. So the question is, do I know that this sampling distribution is bell-shaped? And the answer is yes, because there's something called the central limit theorem. The central limit theorem, I still got ways to go here, okay? The central limit theorem, one part of it says, if I have bell-shaped population, I'm going to have bell-shaped sample mean distribution. So if I know that that's bell-shaped over there for the population, then mathematically I can say my sample distribution will also be bell-shaped. And so I know that the empirical rule will apply to this. But it's more than that, because now I can use z-scores and the normal distribution in order to figure out what numbers are going to happen in my samples. So for example, I could say something like this. What is the probability of having X bar more than, let's just say, 128? Well, if I ask that question, then that means I can draw a bell-shaped curve or a normal curve, and I can say, all right, here's my curve, here's 128. I want to know this area in that tail right there. And I know that this is 120. And so I want to know what that number is. And so what I want us to do is to go through that process. How are you going to make this happen? How are you going to find that area right there? Now it depends on your desire, okay? Some people might use a table, right? Some people might use technology. I think I'm going to prefer to use technology here. So if I go to my normal distribution applet, and I say the mean is 120, and the standard deviation is 1.5, and the thing that I'm looking at is 128, and then I say, what's the probability of that happening? That actually comes out to be 0, because it's so far out compared to what I have. So I better change this, make it so it's not quite that bad. Let's go 126. Oh, still too far. Huh.
The standard should be at
1.5.
Oh, 2.5. Oh, that's why it was not working. Okay. Thank you, 2.5. I knew there was a reason why I was not doing this myself. I have other helpers. So still, it's going to be pretty small. Okay. So now, the situation right now, currently, is if you don't know how to do this, that would be a problem. Because this is what you need to do on the next homework set, is you need to be able to find probabilities based on z-scores using this information right here. So if you have the technology available to you and you say, oh, I have a mean equal to 120, I have a standard deviation equal to 2.5, and I want the probability that x is greater than 126, and I drop all that in there, and I get basically 1%. Okay, that's pretty small. But now we want to put this into better context. What does this actually mean to us right now? What this means to us is, if I have 36 people in the company and I select them at random and I find their blood pressure and I get the number 126, I am very surprised. So then maybe if I'm picking these 36 people randomly, not from the company itself, but let's say I'm picking them from the custodians. And then I would say, hey, I have some evidence that the custodians have a higher blood pressure than what you would expect them to have. So maybe there's something going on here. Because I picked these people at random, I expected them to have a mean of 120, standard deviation of 15, and then when I put them in a sample, it should give me a more accurate representation. But I'm surprised at how high this number is. In fact, anything from 115 to 125 is what I expected, but I got 126. And it's very low probability of happening by chance. This is the entire concept of statistics. We ask the question, could this happen by chance? And we say, no, not really. So then it must not be just by chance. Maybe there's some reason for it to happen. Maybe the custodians are all being fed pretzels or something in order to make their blood pressure go up. Or maybe the executives have more of a healthcare coverage thing, and so then the custodians are being treated poorly. I don't know the answer to that, but if I am doing this right here, I am surprised that this number is so high compared to what I expected it to be. And in fact, I could ask the question, what are the top 3% of sample values that I would expect from this? So what I would be saying here is, if I have a mean of 120, and I'm looking at the top 6%, 0.06, what data value do I have right here? And once again, if I have my software available to me, I have the mean of 120, standard deviation 2.5. I put in 6%, and I get 123.9. So then I would say, okay, this is telling me what to expect from my sample. And now that I know something about my sample, maybe it will tell me something about the population that I took it from, assuming that things are just done randomly by chance. All right, so what questions do you have about this current situation? Yes?
Yeah, wouldn't it be 0.03?
I put in 120 for the mean, 2.5 for sigma, and probability of 0.06 for the right-hand side.
What would it be? Just looking for the top 3%, but if that was 0.03.
Oh, that's what I did wrong. So, you know, the nice way to change this is say, oh, sorry, I haven't clicked. There, yeah, okay.
I heard you say 6, but I didn't see you right.
Oh, so reason number 2, not to do videos just on your own, okay? Find other people to catch your mistakes. That's great. I appreciate it. So, any other questions that I like to answer? Okay, I don't like to answer the question, oh, you made a mistake. But anything else, is there anything else out here? Okay. All right. All of this is for a bell-shaped data set. We are now going to consider a non-bell-shaped data set. And sure, let's use a red marker. Go across like this. And then we need another one, so. So the one that I like to use here is distance from class. Okay, how many of you live less than 5 miles away from you? Okay, 11. How many between 5 and 10? Okay, more than 10? Yeah. Okay, so we're all right. This is not a bell-shaped distribution. There are a lot of people that live within a mile of here. There are some people, though, who live more than 10 miles away. There are people who live 30, 50, and more miles away from class. They're not up, but this is what that distribution looks like. Now, this distribution does have a mean, and it does have a standard deviation. It's not bell-shaped, but let's say that the mean was equal to 5. And let's say that the standard deviation was equal to 9. Since it's not bell-shaped, the empirical rule doesn't work. This might, okay? So, what happens if I use n is equal to 36 and I do a sampling distribution? As it turns out, very similar things happen here as what I had before. So I'm going to look at this and I'm going to say, would I come out with an average of 5 every time I took a sample? The answer would be no. But as it turns out, I am going to get my values to be somewhat close to 5. Once again, you have to think about how this works. If I'm taking 36 people out of a group of a couple of thousand, I'm certainly not going to get them all so that they live more than 10 miles away. But I'm not going to get them all so they only live 1 mile away either, if I'm picking 36 at random. So my samples will be possibly less than or greater than 5, but the mathematical theory tells me that the mean of these averages will be the same as the mean of the population. So I will still have variation in these numbers, but the center of that variation will be the same as the average that I had over here. And the standard deviation of those samples will still be the population standard deviation divided by the square root of n. So what is that number? This will be 9 divided by 6. 1.5. So according to the empirical rule, what will I expect to happen for these sample numbers? Can somebody tell me what I would get if I applied the empirical rule here?
That is a 96.
95%?
5% of your data will fall between 1.5 standard deviations.
No, 2 standard deviations from me. I want to know what those numbers are. 2 standard deviations from me.
Between 2 and 8.
Between 2 and 8. So I find 2 times this, and I add it to 5, I subtract it from 5, and so it's between 2 and 8. So if I have 36 people whom I chose at random, and I ask you, how far do you live from the class? If I find the average, I would be surprised if that number is higher than 8. I would also be surprised if it's lower than 2. Again, all of my extreme values here are not very likely to happen. And so yes, they are going to have an effect on what I do. but it's not going to make my average completely inaccurate. Because I'm taking an average, it's going to reduce the variation. It's going to give me some kind of a picture. It is going to be between 2 and 8. It's not exactly 5. But it's going to give me something, right? Some idea of what to expect if I have 36 people and given this mean and standard deviation, this is what I expect to happen. Except for one thing. What do I need in order to use the empirical rule? I have to have bell-shaped data. Do I know that this is bell-shaped, even though the original is not? Yeah. Kind of. Right? The central limit theorem says for any population and for a large enough sample, then I will get a bell-shaped sample. As my sample sizes get larger, I will have a more bell-shaped curve if my sample sizes are large enough. What's the definition of large enough?
Is it greater than or equal to 30?
Some people say 25. 30 would be good. Larger the better, of course. But if n is greater than 25 or 30, somewhere in that neighborhood, then we're going to say good enough. Now, I've looked at this probably about 4 or 5 times while I've been teaching this class. Where does that number actually come from? How can we say it's either 25 or 30? And the answer is pretty much it's an empirical thing. It's just something that we observe. Because if you have a data set that's just craziness at the beginning, and it's just all over the place, and there's just all kinds of clumps and clusters, and it's just not bell-shaped at all, that's different than something maybe like this, which has a pattern to it, okay? At least it has a pattern to it. It's not just wacko. But we can't know what the population looks like, right, before we look at the sample. But the fact of the matter is, most of the time, if our sample size is somewhere in this neighborhood, then we'll be decent enough information for us to say that this is a bell-shaped distribution of the sample means. Question?
So that only applies to sampling distributions?
This only applies to sampling distributions. If our sample size is around 25 or 30, then the distribution of these averages will be a bell-shaped distribution. Yes. Now, you could ask the same question about things like the median or the standard deviation, or stuff like that. But we're not going to ask those questions right now. We're just talking about the average. Okay, so there. So then, once again, we can do this same analysis. We can use z-scores to figure out things about what's happening here. So if I were to say, what is the probability of X bar, let's say, less than 3? My mean is 5. My standard deviation is 1.5. I want the probability that X bar is less than 3. Should put an X bar in that. So then if I have my software, My little applet is just sitting right here waiting for information. .5. This is 3. Less than. It's 9%. So then I'm looking at this and I'm saying, all right, if I know the average for everybody in terms of their distance from class, and I know the standard deviation of everybody, and then I say, okay, given that information, I went out and I talked to 36 people, and I found that the average distance from class was 3. Well, that's certainly possible for that to happen. There would be like a 10% chance, 9 or 10% chance that that kind of thing would happen. So I might not be surprised by that. But if it were less than 2, I would say, oh, there's something going on here. These 36 people, maybe they don't represent the population at large. And so if I say something like, well, these 36 people are all in student government, then I would say there might be some evidence to say that people in student government have a lower distance from class than other people. Because when I did the sample of 36 of them, it came out to be a lower number than I expected it to be, given the situation that I have right here. So then maybe I'll say something like, maybe student government needs better representation of the outlying areas. You know, I can make all kinds of political statements with that. But it's a question of saying, what can I expect from my sample? And if I get something which is an unusual result, then perhaps the group I took it from is not the same as the population at large, because that's an unusual random thing. But it could happen. And certainly this, it's 9%. Well, sure. I would not be surprised about that. And then I could do the same thing. What would be the top or the bottom 10% of these things? I could do that same analysis. So the difference here is that I start with a non-normal population. And so I have to have a large enough sample size in order for this to work. All right. So what's the third thing? The third thing is when I'm talking about a binomial probability. So let's use something like what percent of the population at Western plays Fortnite? I don't know. Well, let's ask. How many of you play Fortnite? Oh. Not great. A couple, few, right? So let's say 15%. I used to play PUBG, but I'm just not that into it. Now I mainly just do jigsaw puzzles. Less stressful. I mean, really, okay, when you're going around killing people all the time, you know, that's got to do something to you, right? Not to mention Call of Duty and all those other things, right? And you've got all these people dying all over the place because you're shooting at them. You know, it's, anyway. It's a lot better if you're just making jigsaw puzzles. Nobody dies, right? Okay. And in Fortnite, they don't bleed very much. Some people told me they don't bleed as much in Fortnite. So then, is that better? I don't know. You're better able to kill them because they don't bleed. Is that what we want? I'm not sure. So anyway, that's what we're going to pretend that this is the probability. But this is a probability. It's just a probability. But we can still do some understanding of sampling based on this. But we're going to move our sample size up quite a bit. We're going to say n is equal to 400. So I'm going to ask 400 people instead of just 36. Now, if I got 400 people, that's a pretty good amount, okay? But I'm still not going to get 15%. If that's my population number and I'm asking 400 people at random, I'm still not going to get exactly 15%. So, what's going to happen? Well, I actually need a different symbol here now. I need p hat. P with a hat is my sample proportion. So p hat is going to be somewhere above or below this 15%. However, it makes sense, reasonably, that we would say the mean of these p hats would be equal to p. That the mean of the sampling distribution for the proportion, the average of that distribution is the same as the population proportion. Sometimes it's higher, sometimes it's lower. But then we need a standard deviation for that. Okay, so this is then the standard deviation of p hat is the square root of p times 1 minus p divided by n.
Is that all square rooted?
Yes. Now, it's not hard to show this mathematically, actually, but we're going to set ourselves apart and not do that. Okay. But now that we know this, we could use some information to make this happen. So this is 0.15. Let's calculate that standard deviation. I want to take 0.15 times 0.85 divided by 400 and take the square root. And let's go to 3 decimal places here. So hopefully what you got is 0.018. So what does the empirical rule tell us about this? Third time's the charm, perhaps? Maybe the third time we can get this. So we have the right numbers. Anybody willing to go out on a limb and tell me what these numbers are? First of all, it would make sense to say, how would we find those numbers? We would take 2 times the standard deviation, add it to the mean, and we would take 2 times standard deviation, subtract it from the mean. Right? So, Jaron, you're looking like you're able to make this happen. So the top end, if we add, that'd be 0.036 added to that, which would be 186. Okay? How about the subtraction, Jerry? You got that one?
I will in 1 second.
All right, so I'm gonna give you a second.
Which is 0.104 or 100
0.0104.
0.114.
114.
No, 0.114.
Oh,
Right?
you are probably right.
Yeah.
0.114. So what does that tell me? This tells me that if I'm asking 400 people, hey, do you play Fortnite? And I get a percentage that's higher than 18.6%, I would be surprised. I would be saying, wow, this is a den of Fortnite-ness. There's a lot of Fortnite happening amongst these 400 people compared to what I expected it to be. Alternatively, if I got a percentage of 11%, I would say, okay, this is a non-Fortniting place, wherever this is. These 400 people are on the low side of the percentage. This is lower than what I expected it to be. But then we are asked the question, does this actually work? What do we need in order for this to work? We need it to be bell-shaped. How can we know if it is bell-shaped or if it is not? If the square of the standard deviation is less than 10, then p hat is bell-shaped. Oh, I'm wrong. I put the wrong numbers in. Sorry. N times P times 1 minus 1 is great. All right, that works. So then, pretty much what has to happen here is that your sample size needs to be pretty large, because if your P is somewhere around 0.5 times 0.5, then that's like 0.25. And so if you take 10 divided by 0.25, that would be 40. So you've got to have something that's bigger than 40, and usually, if you want a decent answer, you want something around 300 or 400 in order to get some reasonable amount of accuracy to your stuff. So then, we can now determine probabilities of what we would expect to happen. So if I were to ask the question, what is the probability of p hat greater than 0.8? Well, what would that look like? Our mean would be 0.15. Our standard deviation would be 0.018. And we would want the probability that p hat is greater than 0.18. And we would put this into the normal distribution. So we would have 0.15, 0.018, 0.18. That would be about 5%. So again, that's kind of surprising. 18% or higher. Now, what I have just shown you looks very much the same as what we had before. The difference is, for the first two situations, we were actually measuring a number. I was finding the blood pressure. I was asking people, how far away do you live from this thing? But in the third situation, I'm not asking you a number, I'm asking you a question, yes or no. And so it's a different kind of measurement. And I'm getting this thing, which is the proportion of the people, which is not the same as these other two measurements. However, just like before, I have a bell-shaped sampling distribution. And since I have a bell-shaped sampling distribution, then I can use z-scores to analyze the situation and figure out what I should expect to happen. And in fact, it's a little bit easier down here because I don't need an actual standard deviation from a data set. All I need is a general probability to go from. Once I have the general probability, I can, and my sample size, I have to know that, the general probability and my sample size, then I can know how much variation to expect in my data. And then I can know what is most likely to happen in this kind of situation. So it's actually a little bit easier and better when I'm using proportions compared to using mean and standard deviation. Because most of the time, I don't actually have the population data. I don't know the mean and standard deviation of the population. So it's not really going to work. This, however, has better chances of being correct. Now, if you think about this kind of carefully, you can see that this third situation is similar to finding not p hat, but finding x given n and p. What happens here is that we use the formulas that we had previously. The mean is equal to n times p, and the standard deviation is the square root of n times p times 1 minus p. This thing that we have here is mathematically the same as what is in this third section. So if we wanted to, we could use the x, which is the number of people that are actually in the situation. Instead of using p hat, we could use x. But having gone through all this complicated stuff, it's usually easier for us to then say, and I'll put this over here, p hat is equal to x divided by n. So that when you have a situation where they're asking about numbers of people, you can convert from numbers of people into sample proportion when you take x divided by n. And then you can use all this stuff that we have here. All right. That should do it. So your homework then will consist in these possibilities. Answering questions about when can you do these, and then once you know that you can, Then you use z-scores to analyze them and figure out if it's likely to happen or not. All right, that's it.